In this video, you will learn about the shapes of hydrocarbons, that is alkanes, alkenes, and alkynes, the intermolecular forces of attraction in them, and their physical and chemical properties. So if you look at the shapes of these compounds, alkanes, the carbon here is forming 4 single covalent bonds. And that's for each carbon. So this carbon here is surrounded by 4 single covalent bonds, and therefore it's a tetrahedral shape. And the second carbon is also has 4 single bonds, and it's a tetrahedral shape. For alkenes, there is at least 1 double bond. So carbon 1 forms a double bond and 2 single bonds. And these bonds are arranged in a trigonal planar shape. The same is for carbon 2, which forms a double bond and 2 single bonds. And if you look at carbon 3, this carbon is forming 4 single covalent bonds, and therefore the shape would be tetrahedral. Alkynes have at least 1 triple bond. So there's a triple bond between carbon 1 and 2, and the triple bond and the single bond with the hydrogen is planar. So carbon 1 and carbon 2 have planar shape. Carbon 3 and carbon 4 have tetrahedral shape. Now let's look at the intermolecular forces of attraction in hydrocarbons. Alkanes, alkenes, and alkynes are non-polar molecules, irrespective of the length of the carbon chain. Therefore, the only intermolecular force of attraction are weak dispersion forces. Now, dispersion forces depend on 2 factors. The main factor is the molecular mass. Greater the molecular mass, greater would be the dispersion forces. In this example, the molecular mass of propane is much lesser than that of pentane, and therefore it will have lesser amount of dispersion force. If the molecular mass is the same, the molecule with more surface area has greater dispersion forces. Now in molecules, branching reduces surface area. So if you look at the isomers of C5H12, the straight chain pentane has the greatest surface area, and therefore it has maximum dispersion forces than 2-methylbutane, and 2,2-dimethylpropane has the least surface area. Now let's look at the physical properties of hydrocarbons. One of them is solubility. Hydrocarbons are insoluble in polar solvents like water because they themselves are non-polar. Therefore, they are soluble in non-polar organic solvents. Regarding their meltings and boiling points of all the hydrocarbons, that depends on the extent of the dispersion forces of attraction between the molecules. Hydrocarbons with higher molecular mass have greater dispersion forces, and therefore the melting points and boiling points are higher. Therefore, the boiling points and melting points steadily increase from methane to butane and higher alkanes too. In this example, the molecular mass of both the compounds is the same, but there is greater branching in 2,2-dimethylpropane. Therefore, its melting and boiling point is lesser than 2-methylbutane. Now let's look at the chemical properties of alkanes. Alkanes are stable compounds and have low reactivity. So they undergo only 2 main types of reactions. One is combustion and the other is substitution. Combustion could be complete combustion, And this is when the alkane reacts with excess or plentiful supply of oxygen to form carbon dioxide and water. For example, butane reacts with oxygen to form carbon dioxide, water, and heat is released. It is an exothermic reaction. Sometimes there's a limited supply of oxygen, and that's incomplete combustion. Here, butane reacts with oxygen to form carbon dioxide, water, and also some carbon monoxide and unburnt carbon. In substitution reactions, alkanes react with halogens, mainly with chlorine and bromine, where one or more hydrogen atoms are substituted by the halogen. And this reaction occurs in the presence of ultraviolet light. So, for example, if you have a compound like propane, it reacts with chlorine to form chloropropane and hydrochloric acid. Now, chloropropane further reacts with molecules of chlorine, and the reaction continues till all the hydrogens are substituted or the halogen gets used up. Now let's look at the chemical properties of alkenes and alkynes. Alkenes and alkynes are more reactive than alkanes. Now this is because the double and triple bonds are electron-rich sites. That is, they have 4 electrons and 6 electrons between the carbon atoms, making them electron-rich. And the double and triple bonds are weaker than single bonds, so they break easily and react readily. They undergo 2 main types of reactions: combustion reaction and addition reaction. The products of combustion reaction, complete or incomplete, are similar to combustion of alkanes. So here are 2 examples. Propene undergoes complete combustion to form carbon dioxide and water, while butane reacts with oxygen to form carbon monoxide, carbon dioxide, unburnt carbon, and water. Regarding addition reactions, unlike substitution reactions in alkanes, no hydrogen atoms are substituted. The double bond simply breaks and atoms add on to the alkene or alkyne. For example, hydrogenation, which is the addition of hydrogen in the presence of nickel or platinum or palladium as catalyst. Here, the alkene or alkyne adds on a molecule or 2 of hydrogen to form an alkane. For example, in ethene, the weaker bond breaks and forms ethane with the addition of hydrogen. In propane, both weak bonds break to form propane. Lindlar's catalyst could be used instead of nickel. Here only one bond in the alkyne breaks and the end product is an alkene. Lindlar's catalyst is a mixture of palladium, calcium carbonate, and lead ions. Another type of addition reaction is hydrohalogenation, that is the addition of hydrogen halide. For example, hydrochloric acid. So when hydrochloric acid is added to an alkene or an alkyne, the final product is a chloroalkane. There are 2 possibilities here. If it is a symmetrical alkene, that is, the double bond is in the center of the molecule, then only one product is formed. For example, if hydrochloric acid is added to 2-butene, then the final product would be 2-chlorobutane, and that's the only product formed. However, if it is an unsymmetrical alkene, that is, the double bond is to the side of the molecule and not in the center, then there are two possible products. And if the double or triple bond is in the corner of the molecule, where one carbon across the double bond has one hydrogen and the other carbon has two hydrogens, then Markovnikov's rule applies. The rule says that the hydrogen of the hydrochloric acid will preferably combine with the carbon with greater number of hydrogens, and the chlorine will combine with the carbon with lesser number of hydrogens. That is, the major product in this example, where 1-butene reacts with hydrochloric acid, is 2-chlorobutane, and the minor product is 1-chlorobutane. Hydration is another example of addition reaction, where alkenes react with water to form alcohols in the presence of dilute sulfuric acid. For example, ethene reacts with water to form ethanol. And if it is an unsymmetrical alkene, then Markovnikov's addition applies, and the major product here would be 2-propanol and the minor product is 1-propanol. Lastly, alkenes and alkynes undergo halogenation reactions, which is the addition of halogens. Halogens would be either chlorine, bromine, iodine, or fluorine. For example, if chlorine adds on to an alkene or an alkyne, the end product is a chloroalkane. Here, if chlorine adds on to 2-butene, then an atom of chlorine adds on to the carbons on either side of the double bond, giving a dichlorobutane. Or if it's 2-butyne, then 2 molecules of bromine will give a tetrabromo product. So in the workbook, you'll get to practice questions on the physical and chemical properties of hydrocarbons. So good luck and enjoy.